Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, let's get started. It is my greatest pleasure to welcome Mianwei to come back and have an interview with us. Mianwei has been an outstanding intern with ISRC before, and he's graduating this summer, I hope. Yeah. And his work is on the entity-centric search. And so this happens to be the area that we are focusing a lot. So we are very happy to have him to come and tell us what he has been doing. So without further ado, Mianwei.
Okay, thank you. Thanks, Gongsun. Yeah, so thank you for coming to my job talk today. So I'm very happy to share my work in my PhD study to you. Yeah, so topic as show here is about the entity-centric search querying by entities and for entities. So should I speak louder or this voice will be fine? It's okay. Okay, sure. Yeah, so nowadays the web has become a very huge database that's storing all kinds of different entities. So by entities, I mean for example, like person, like products, like company, all the things are entities. And because of this, most of the information retrieval operations on the web right now are also related about entities. People are searching all kinds of information, for example, for latest event for some person, some phone number for some company, some historical fact. So all these kind of information retrieval operations are all entity-centric. According to some statistics reported in the previous work, like 72.9% of web queries are actually entity-oriented, and 71% of web query contains the named entities. Well, in order to get the information, so nowadays people still get used to use search engine. So as the traditional search engine framework, people will use keywords to characterize what they want. And then the search engine will return a lot of documents. But we also find that this kind of searching framework cannot well support this kind of entity-centric search operations. So for example, like given a query like when did Michael Jordan graduate, if in terms of input, if the search engine are not aware of that, this query actually is trying to search for an entity and also have some entity involved in this query, then it may not be able to better judge which result is correct. And also, for example, you use the keywords, usually you have some ambiguity issue there. And in terms of result, for those kind of operation, when people try to search some particular entity, directly returning a document may not be a good option as well, because the users have to look into the document to find the answer. Yeah. So in my PhD study, actually, I try to focus on, we try to move beyond this kind of traditional information retrieval framework. So we want to study when the concept of entity involved in the input query or in the output result, how can we actually change this kind of search behaviors, search ranking result or something. So here I use a diagram to show the position of our work. So use the x-axis to show the input and the y-axis to show the output. So in this way, traditional IR will become in this inner area. And what we will study is to study when the concept entity appear in the input or output. So we call this kind of operation entity-centric search operations. So specifically, according to whether the entity appear in the input or in the output, we can further categorize these kind of search operations. So if the concept or entity appear in the input, usually people will know some entity and then they want to find some information about this entity. We call this kind of operation is querying by entities. For example, find some latest event for some person, for some useful review for some product. And in contrast with querying by entities, we also have querying for entities. That means the output of results should be that means the users will expect the output result contains the entity. And in this case, for example, want to find the highest building in the world or the most expensive handbag or something like that. Yeah. And you can also see that these two areas have some overlapping area. So in this kind of operations, people usually try to search some entities that match some desired relation for our input entities. So it's a query by and for entities, for example, like the phone number of some company, some year or graduation year of some person. So this will have the entity involved in both the input part and also the output part. So basically, my research work can fit into these three categories. Yeah. So for the querying for entities, we have some work about data-oriented content query system. Querying by entity parts, we have the entity-centric document filtering. And the overlapping area, we will have the relational entity search. And in this talk, actually, I will specifically focus on this area, this work and this work, the querying by entities work and the querying for entities work. For the relational entity search, although we have some publication, but right now I'm still actively working on that. So I will briefly introduce it in the future work. So this is going to be the overview of my talk today. I will start with the querying for entities and query by entities, and then followed by our future work. Yeah. This is pretty much the overview of my talk today. So let's start with the querying for entities part. So the position of this work is here. So in this work, we try to design a general data-oriented content query system. Try to support searching directly into the document for finding the related entities. The input will be some keywords, the output will be some entity. The motivation of this work is that, so nowadays, we are actually witnessing many different kinds of efforts trying to search entities inside the text data. So for example, the type entity search proposed in 2006 tried to use some keywords to directly return entity as a result. Like web information extraction, people would try to use some simple pattern and then use some idea like snowball to iteratively get a lot of relational data from the web text. Like web-based question answering, people given some question as input that they want to find some answer directly as a result. Well, you can see that these kind of different efforts are all doing similar stuff. They will have different keywords, they have different patterns, try to find out some entities inside the text data. That belongs to the querying for entities applications. Well, since this project are developed independently, so these kind of like keywords or patterns or scoring function are all hard-coded in their projects. And as their limitation, so the project we developed before, one project cannot be used easily in other projects. So how can we, so the motivation of work is that can we do a more general system to better support these kind of different applications? So this is the goal of our work. Since they are doing similar stuff, so we want to build a general system that can better support this kind of different querying for entities application, for query for entities projects. So this my idea actually is much similar to database. So before database is invented, people, when they try to do some data managed job, right, they need to write the data storage, data indexing in different projects. And then the invention of DBMS actually largely facilitate their jobs. So similar here, we want to try to build a general system to better support this kind of different querying for entities applications. So how this system should look like? Couple of requirements. As I have mentioned before, different projects actually will have different kind of like entity extraction and different kind of scoring function to find out the correct entities. And also they need to support different entity types. So specifically, we require that in order to build a general system that should support a very flexible entity extraction their scoring function should be customizable for different applications. And their entity type should also be extensible. Every time when we try to support some new entities, we don't need to change the project code. We can directly extend it easily from in the system. So this is the purpose of the requirements of our system. So to handle this, actually, our solution is kind of a relational model. The key idea is that we try to view these kind of keywords entities as a lot of tables in the corpus, in the back end. And then we'll build a system beyond that. And then we design a language to query that and find the result return the result as kind of a table result. I know it's a little bit unclear here, so I want to show you a demo to see how actually it works. So this is a system that I developed for this project. And here's the interface. This system is built based upon the This system is built based on a Wikipedia corpus and have some entity types extracted and indexed in the corpus. And then it supports a query language to query those kind of entities, for example, like person, location in the text data. So how it will work? For example, I write a simple query first. So for example, I want to find all the person entity from. We like to have some pattern here. And then say we want to find all the person that which have the computer science, this kind of noun phrase appear close to it. Then you will process it and then get all the entities that match these kind of patterns. So this is the idea. So we can write some different kind of patterns here, and then to specify what kind of entities we want. So here use the brace, which means that is the computer science is a sequential phrase. Here use the square bracket, I means that is the kind of window pattern. Yeah.
With this person?
Right now, no. So in ranking, we need to have something like group by, order by. So yeah, wait a minute. So I can first show how this kind of entity match the. So you can see, I can say a context function. I can see how they match our patterns. So for example, like here we get the person name, and then we see how the computer science, this kind of word, appear around it. So this is just some simple patterns to that. And then also, if we want to support the weighting, we need to order the result. So for example, showing a query here. So in this query,
I don't see any connection between merging with computer science in this supporting solution.
So yeah, so computer science. So I don't know, just know I have a person here. So yeah, it's no connection, but I just say we'll collect. So this is basically a collecting phase. Use the whale pen.
What does context mean?
Context means that we show that, for example, Virgin here is a person name here, computer science.
Oh.
We try to find all the kind of entities that match that would have this word appearing around. Yep.
10 means that they are 10 words apart?
Yeah, 10 words around. Yeah, 10 words apart. Within 10 words, actually.
What's the raw data?
Raw data is so this actually is a smaller demo. So this demo is just built on the Wikipedia corpus. I think it's a 2009 Wikipedia corpus. We have a larger data set. We have a larger system built on a large data set using CRUD web data. That one is bigger.
So the context is the document, and the person is the title of the document.
The person is the entity I want to extract. Here, for example, I extract a lot of entities from this kind of context here.
For the first sentence, that you actually didn't understand, right? Because this is a paper that written by this guy.
Yeah.
Unfortunately, this journal is like monographs in computer science.
Yeah. So this is not rank result. This is just some snippet that match this pattern only. Yeah. So if we want rank result, we still need to do some aggregation and ranking. So for example, here, I would like to find the population of China. Then maybe I write some simple pattern, population of, and then close to China. And then I can do some group by, for example, because those kind of entity that match appear frequently will be more likely to become the correct result, right? So do some aggregation, and then we can do some ranking.
So you have all this kind of table constructed, and then you use this kind of.
Yeah, things like that. But actually, in the back end, it's not table. It's just still like inverting index. Yeah.
So in this way, you cannot support like natural language questions.
So no. So this I just say this is a general system to better support this kind of project. So it's a kind of like database actually. Yep.
So what are the key technology here? The key technology is how do you feed the inverted index, or how do you extract entities, or how do you put the interface together, put the system together?
Yeah. So I think in this talk actually I didn't go into the details of those technique. So
Right.
but in the paper the key technique is like, for example, when this kind of pattern becomes very complex, what kind of key inverting index I need to choose?
Okay.
So query plan and also which index should be used. Yeah. So this is a general idea. So basically try to support querying the entity inside the text data. So yeah, I think I already show. So how it will work actually is just like for each kind of occurrences of the keyword or entity, I just view that as a table. Things like here, we have its position, we have span, we have some confidence like measure whether this kind of extraction is correct or not. We have store this kind of information in the inverting index. And then given some, so as I said before, we need to fulfill two requirements, right? Flexible entity extraction, customized scoring function. So how can we do that? So basically, so use a relational model. For example, we are from class to specify which entity we want. Use some pattern to filter some result. Use some aggregation to aggregate the result that frequently mentioned, and then some customizable scoring function we can use to rank the result. So basically, it's a general system to support it. And another interesting idea for this work is that I mentioned about the third requirement, extensible entity types. So in a lot of projects, when we try to support new entities, they need to rebuild the index, do a lot of other things. Well, for this project, we use an idea of view, the concept of view to the view concept from database to support extensible data types. So like the example shown here, we already indexed the number, location, person, right? But we can use the idea, for example, we specify some pattern to characterize a number from to define a population type from a number type. So I can show an example here. So here you see we define a population of a number, but we can also divide it as a view, like here. We can specify a lot of different kind of patterns, like inhabitants, population of, and define this population as the number. By doing that, then go back to the query. We can directly query the population directly. Although these kind of entities are not indexed in our backend system, but we can still query that and then get the same result. So this is the kind of like virtual entity types from the existing types. And define this type actually is pretty easy. We're just going to write some like some type here, and then simply save it. It will appear in the left part, and then you can directly query that. So yeah, so let's define some new types, new entities based on some existing entities. Yeah, so this is the requirements, how I will fulfill this kind of requirements in our system. And then the main technique, so yep.
So I have some question about your definition of entities. What do you mean by entities?
Entities, so that's the system here. So in our system, we will pre-extract some entity and index that in the backend. For example, we extract the number, location, organization, location. These are all very basic entities. So I define some high-level entity based on this basic one.
So you use NER, right? NER package.
Yeah, NER package to extract that. Yeah, and also this demo already show these 4 types, but in a larger type, I use a lot of dictionary to match more entity types. Yeah.
So the population you extracted, is it a new entity? Is it a new attribute of the existing entity?
It's a new entity based on the number, this basic entity. The number is pre-extracted and indexed, but while the population is not indexed at all. we just use this kind of pattern to extract a new type. To extract those kind of numbers that are more likely to become an entity. Yeah, so some new entity types based on the existing types, existing entities.
So I have one question. So what kind of problem cannot be solved by keyword search and can be solved by this demo?
Oh no, I just say this is just a back-end system to better support those kind of projects. I didn't say I solve a new problem. I just built a general system to better support them. So they don't need to write too much code for their projects. Yeah. Okay, so this is the first piece of our work. So as I say, the main technique focus on the index design. How can we build an inverting index for those kind of keyword entity to make this kind of querying faster, and also some query optimization, which keywords to be used, which entity should be searched, something like that. Yeah, so this part I wouldn't go into the details. So if you have questions, we can discuss offline. Yeah, so basically this is the first piece of our work. It's about querying 4 entities. So our work is about data-oriented content query system. So the second work I'm going to introduce is this part. And this will be the main focus of my talk today. It's about entity-centric document filtering. The idea here is that we try to input some entity and then we want to output the document. And then the problem is that we given an entity which is characterized by an identification page. How can we identify relevant documents? So entity-centric document filtering. So as I have introduced before, many kind of information retrieval operations on the web are searching information, searching documents about particular entities. For example, for common people, they might want to know those kind of latest event for their favorite celebrities. For some business people, they want to know that, for example, after they release some products, they want to know some feedback or review of their products. So recently, they also recently proposed the track task. It's about knowledge-based acceleration. They want to help Wikipedia editors to identify which kind of documents are relevant for some particular entities, and then help them to enrich the content of Wikipedia in a fast manner. So we can see that all these kind of scenarios are all about querying by entities. They want to find documents that related to entities. So the goal of our work is try to build a system to better support this kind of, to facilitate these kind of applications. So in order to build this system, what information do we need? The system needs to know what kind of entity we want, right? They need to know the information about these entities. And we will say that actually using the entity name is usually insufficient because it can be very ambiguous. Given Michael Jordan, it can refer to different people. So in our project, our idea is that we will try to directly give some page that characterize these entities as input. So for most of the entities in the world nowadays, we will have some pages on the web characterize this entity. For example, for movie star, we will have IMDb page. For product, we will have their specification page. For academic people, we will have homepage, or popular entity, we will have their Wikipedia page. We will have some descriptive page that characterize this entity. So using these kind of things as input will have 2 advantages. One, first, it definitely resolves the ambiguity problem. And second, it also provides more information about this entity. We can better have the system better understand the input query. And in terms of output, given some entity, we will try to know what kinds of documents are relevant or irrelevant for this entity. So this is a simple example. For example, for the first one, this is relevant. Well, the second one is irrelevant because it's mainly talking about Steve Jobs instead of Bill Gates. And similarly here for Michael Jordan, the first one is related, while the second one is unrelated because it refers to computer science people. So the input will be a page that characterizes.
The page with this entity name.
Yeah. Characterize this. Yeah, but you know that I should define this one, this kind of relevance or irrelevance is pretty subjective. Different application, different labeler even, they will have different criteria. So in our work, we try to learn that from user labels instead of like define some criteria for whether it's relevant or not. Yeah, so this will be the input, this will be the output, and this will be the problem we will study. Given a query page, lot of documents, we want to find which one is relevant or irrelevant. We say this is called entity-centric document filtering problem. Well, this will be the problem we will study in this work. So why this problem is challenging? Because like the key challenge of this problem is that we will have a very noisy entity page as input. The query is very long. So let's see the traditional IR. Usually in traditional information retrieval, what people will do is like usually they only use these kind of very short keyword queries. A keyword query only contains 1 or 2 keywords or 1 sentences. And then people have already developed a lot of information retrieval models for these scenarios, like BM25 language model, vector space model. They all work pretty well for this kind of short keyword query. However, at the same time also, people has also observed that this kind of information retrieval model, usually their performance will degrade when the query becomes longer. For example, consists of like 2 or 3 sentences. When the query becomes longer, this kind of IR model wouldn't work well. Well, in our problem, it becomes more difficult. Our query right now becomes a very long page. It's not just a few sentences, it's a very long document. So, and in this document, definitely it provides a lot of information about this entity. However, at the same time, it also includes a lot of noisy keywords, which may not be that relevant with this entity. So in this case, definitely traditional information retrieval model wouldn't work very well here. So this will be the key challenge we will focus in this work. Yeah. The noisy query page as input. So how to solve this? Instead of directly proposing some solution as some quick solution, we actually start with investigating the fundamental principle actually behind document scoring. It's a very simple question. Given a query, given a document, how can we judge whether a document is relevant or not with this query? Answer is that we need to check the content, right? Basically, we need to check how this document contains keywords that are important for this query. It's very straightforward, intuitive idea. We call this as a document scoring principle. The relevance of document depends on how it contains keywords that are relevant for this query. Yeah. But actually, you might notice that this kind of very simple the principle, it actually contains 2 questions. First, which keywords are actually important for this query? So in this scenario, for example, like Microsoft, Bill Gates, these kind of keywords will be very important for this input entity, right? And second question, how the keywords are contained in the document. So usually we will see if this kind of document contains more important keywords, it's more likely to become a relevant document. So it actually can be decomposed into 2 questions. And traditional non-learning scoring model actually fulfill this principle quite well. For example, like BM25 language model, they actually follow this kind of principle. Like for example, which keyword are important, they will assume that those kind of keywords that appear a lot in the query and less in the whole corpus will be more important keywords. Those high inverse document frequency keywords will be more important keywords. And how they are contained, usually this kind of model will count the term frequency in the document, right? So this is how traditional non-learning scoring model actually will do that. But we will say that actually this kind of the simple answer for these 2 questions actually is insufficient for our scenario. So different from traditional information retrieval, right now our query becomes a long page. So simply using IDF is not enough. in order to identify these kind of important keywords, we need to make use of more other information. For example, like we need to see this keyword, how it appears, whether it appears in the title or in the info box or in the opening paragraph. We have more information to leverage to identify which keywords are important for this entity. And similar here, because our target document is a web page, and web page is also somehow structured. We'll have its like title, we have URL and anchor text, and also something like a picture word. So there are also a lot of other information to characterize how these kind of keywords are contained in the target document. And once we want to incorporate more information, about these kind of questions, then simply manually fulfill the principle becomes impractical. And because of that, we will think about, is it possible, can we try to learn to answer these two questions? So it's very natural to think about learning to rank. Well, when we look at learning to rank, we found that actually traditional learning to rank actually fails to learn to fulfill this principle. Right now, nowadays, the academic community has already proposed many learning to rank models, like Rank SVM, LambdaMart, RankBoost, a lot of different kind of learning to rank models. And all these kind of learning to rank model actually follow the same abstraction. They try to learn a ranker for a query and document. And then they will have some input features to characterize that, and then they try to output the document relevance for that. And from this abstraction, we can see that actually this kind of abstraction doesn't learn to fulfill our principle. Because in the principle, the most important concept is keywords, how the keywords appear in the query, and how the keywords are important for the query, and how the keywords are contained in the document. The concept of keyword is not modeled in here. And so how this kind of learning to rank model actually score the document?
I'm sorry, what do you mean by keywords here?
It should be, keywords means like maybe I should use the words is better. So it means like the word in the query, each word in this query, and this kind of word appear in the document.
And why is not appear in the document?
Why it's not appear?
You said keyword is not.
So a keyword not appear in the abstraction, this abstraction. So this model abstraction, we only have query and document. We don't model the word, the concept word here. Yeah.
So, but I can say that you can model that in the teacher function, right?
Yeah. So that's my point here. So in order to make this kind of system to work, they need to use this kind of feature, BM25 language model, right? They need to, in this feature design, they need to characterize how the document contains keywords from the query. So actually, they require the designer to fulfill the principle in the feature design. Yeah, instead of learning that. So, and as we have seen that before, for some scenario, manually design this kind of features, manually fulfilling the principle is difficult. As I have claimed before, because the query is complex and the document is also complex, then manually design this feature is difficult. So this kind of traditional learning to rank framework just simply leave this burden to the feature designers. So it's not good. So that's why I claim that they didn't learn to fulfill the principle, but simply leave it to the designers. So, so the purpose of our work here is like, question? Okay. We try to facilitate the feature design for people. And the first important concept we propose here is called the feature decoupling idea. The key idea is that traditional feature design, they need to describe how document contains keywords that are important in the query. And we say it's difficult because like in this feature design, people need to address these two questions together in the feature design. So our intuition is that actually we can decouple this feature design into two types of more elementary features, such that one type of feature addresses one type of question, one question at a time. So this kind of feature will become much more easier to be designed. So this is a key intuition of our work. We try to decouple the features into two directions. One is for meta feature, characterize which keywords are important, and intro feature, characterize how the keywords are contained. Yeah. So here is some example features. for our entity-centric document filtering. Example feature can be like, for example, general feature like IDF can be used in the meta feature for the query side. And this, whether this keyword is a noun, is a verb, is mentioned in the entity or not. And also have some structural features like the position of this keyword in this page, how they are mentioned in the info box. They are all meta feature, the query side features. Similarly, we can define the intra features, how the keywords appear inside the document. So for example, different position in the URL, in the title, different position of that, and different representation. Besides like simply counting the term frequency, we can have a log scale TF, normalized TF. We have different kind of term frequency representation characterize how the keyword appear in the document. Yeah, so this will be the example feature design for our applications. And because of this decoupled feature, we are facing a new learning to rank framework. So in the, yep.
Yep. So essentially, the left-hand feature are like query level features.
Query level feature.
The right-hand side is query URL features.
A document feature.
Query document feature.
Keyword document feature. Yeah, I think so.
So you can also put VM25 and all these features in the intra feature as well.
VM25, I think you already combined the keywords inside the query. VM25, yeah. So it's a summation of all the keywords inside the query.
Right. I'm saying that you can also put it there, right?
I think so. The feature, meta feature will be F, W, and Q for the query, word query. And then for BM25 is like the feature defined on document query already. So this BM25 will correspond to our traditional learning to rank features.
Yeah, but for each of the words, you can treat it as a query term and sum over all the terms. It's going to be a BM25, right?
Yeah, you can say that. But BM25 usually is the sum of over different keywords in the query. Yeah, all the keywords. Usually, this is how BM25 is designed. Yeah. So here, just like this one is designed over one single keyword.
And this is a query level feature. You're talking about the query.
Yeah, it's also a keyword part. You also define over one keyword at a time.
I think what you mentioned is the right part is only document level, right? There's no query at all.
No query at all. Cool. Only the keyword and document. How the keyword appears in the document. Yeah. And this part is the keyword to query.
Can I assume if there is no overlap between, there is no keyword overlap between left part and right part, you can learn nothing. You just learn nothing.
So usually when we are doing an information retrieval task, we will see how the document contains a keyword only from the query. So if this keyword doesn't mention in the query, usually we didn't count that, right? Yeah, so yeah, basically we just find the overlapping keywords between the query part and the document part. Yeah. So yeah, the basic idea is just like we just try to decouple the feature design. And then we will have a new learning to rank problem. So this setting is still like traditional learning to rank. We have some query and irrelevant document for this query. And then given a new document, also characterized by a Wikipedia page, we want to judge whether a document is relevant or irrelevant by learning this model. This is pretty much similar to a traditional learning to rank. Yep.
So there's one assumption that you didn't mention. So, so like, is the keyword exists for the query independent of the documents or not?
Independent of the document.
So like for the page Bill Gates, the keyword is always Bill Gates and Microsoft, independent of the documents. Or you are going to dynamic generate keyword, depends on a different document collection.
Actually, no. Yeah, I just check those kind of So given a document, I already check those keywords that mentioned in this document and also appear in the query. That they are overlapping keywords. Given the query and document, I will check their overlapping keywords.
Okay.
Yeah, but yeah, definitely we can extend it. For example, given a query, we can extend more using some synonym or other techniques to find more keywords related for this query. We can also do that. Yeah, but I say, so because of the decouple feature, we'll have a new learning to rank framework. So in this time, for the query and document pair, we describe by two types of features instead of one feature function like before. Yeah, so how can we solve this kind of decouple feature-based learning to rank problem? Will be the focus of our work. Since they are decoupled, so we need to recouple them back. So let's revisit the document scoring principle. Relevant document depends on how it contains keywords that are important for the query. Mathematically, we can translate it to here. The relevance of a document to a query can become a summation of the contribution of each keyword for this document and for this query. Yeah, this will be the keyword contribution for the query and document at the same time. And what I mean recoupling is that how can we define this function based on the meta features and the intra features? This will be the focus, the first requirement in our learning to rank framework. And then the second requirement is that this kind of function should be noise aware. So as I mentioned before, the key challenge is that our query is very noisy. So this contribution function should be aware of those kind of noisy keywords. So how can we solve fulfill these two requirements? The second concept we propose is called the inferred sparsity idea. The idea is very straightforward. Because this query is long, so they will have a lot of overlapping keywords. And this kind of noise, a lot of keywords are noisy, but may not be related with this query. And because of the existence of this kind of noisy keywords, if we just assign some low value to these noisy keywords, their score might accumulate it, and then as a result, they will affect the final scoring accuracy. So because of this, we will require that for those kind of noisy keywords, they should fulfill the requirement satisfying contribution. This contribution function should be equal to 0. We call this is inferred sparsity. What?
How do you determine if it's a noisy keyword?
Yeah, this is a good question. Actually, I will mention that because we don't have keyword labels, say this is noisy or not, right? So yes, this is a typical key challenge I need to handle in the later solution. I will introduce it very soon. Yeah. So I first introduce why this is called inferred sparsity. Because it's pretty related to traditional sparse learning. In sparse learning, people, in order to select features, in order to improve the accuracy, prediction accuracy, they all will require that for the feature weighting, they want that those kind of feature weighting to be very sparse. Only the important keywords will have non-zero weighting, while on the important one, they should have 0 value. And similar here, we want our contribution function to become non-zero only for those kind of important keywords. So they're actually pretty related. But they are also somehow different. So for traditional sparse learning, alpha here is a feature weighting, is a free parameter. So they can directly make it sparse by using techniques such as L1 regularization. While here, the function we want to specify is the target we want to specify is a function instead of a free parameter. This function actually is defined based on a lot of our meta feature and decoupled features. So traditional technique wouldn't work well in our scenario. So to achieve this inferred sparsity, our key idea is that we will use a 2-layer scoring model. So basically, I will try to learn a keyword classifier to judge whether keywords is important or not. So here, C means a keyword classifier. If it equals 0, means it's noisy keyword. And then if it's important, that means that you will have some non-zero value. And based on the output of this keyword classifier, we further determine its contribution based on how it appear in the target document. But trying to design this model is not that easy. As you have mentioned, we don't have keyword labels here. So it's not easy to learn the keyword classifier here. And also, how can we design a feature to determine these two aspects? Yeah, so how can we solve it? Our solution is to use a graphical model, a restricted Boltzmann machine model to handle that. The general idea is like this. Given a document, we try to use the random variable y to denote whether this document is relevant or not. And then you will connect to a lot of keywords. It contains a lot of keywords, right? So for each keyword, we'll also have a variable denote whether this keyword is an important keyword for this query or not. If it equals to non-zero value, that means that it's important. If it equals to 0, that means that this keyword is a noisy keyword. And then we'll have a couple of 3 types of different factors to determine how this kind of keyword, how to define the keyword classifier, and then also how the keyword contribution should look like. So first, we have a keyword classifier, right? So we will use this factor to represent that. Basically, according to our definition of features for meta feature, we use meta feature to characterize how the keywords are important for the query or not. So here we will use this factor to incorporate this information. And this part will represent the contribution of a keyword to the document. So if this is important keywords, then we will further look at how it appears in the target document. So we measured it here. And if it's not important keywords, then this kind of keywords should be eliminated. So it should not contribute any score to the final document relevance. So we have 0 here. So basically, it's a Markov network design. And we also have document factors. This part we can try to incorporate traditional learning to rank feature, for example, page rank, document length, or even BM25 vector space model. We can have this kind of traditional features incorporated in this factor. And then our algorithm just try to solve here. So this design actually well handles the lack of keyword labels problem, because we can simply view this part as a hidden variable. And then based on the document labels only to learn which keywords should be important, and then also as well as like how they should contribute the score to the final document relevance. And the key advantage of this model is that it's a tree structure actually. So when I try to solve this problem, try to optimize this model, we can use the belief propagation to efficiently fulfill this. So this is the key idea. Yeah. So what I want to claim that, so to make a summary, in our technique, there are 2 important ideas. The first one is called the feature decoupling idea. Try to decouple the feature design such that people can easier design the features. And second is the inverse sparsity. We can we can filter those kind of noisy keywords and only use the important one. And we say that actually this kind of framework is a very general framework, can be applied to other applications. So for example, like use the recommendation system. Try to recommend some items for users. Usually, we can have a similar called item ranking principle here. Because like we can connect the user and item by their attribute. Usually, when we try to measure whether this item is good or not for a user, right, we will see how this item match the attribute that these users are interested in, right? So they're connected by the attribute. So the user here becomes a query, attribute becomes our keywords before, and items becomes the document. Similarly, we can have a lot of meta feature and the intro feature to characterize these 2 links. For meta feature, we can characterize how the users like this kind of attribute. For example, some long-term preference, some short-term preferences, how his friend like this. Different kind of feature to characterize how he or she like this kind of different attributes. And for intro feature, we can similarly have the intro feature for the item attribute. For example, do we have the exact value for the attribute, or we just have some estimated information, or whether this value is missing or not? We can characterize all these things as some feature vectors. And so I also investigate try to apply my work to domain adaptation framework. So here is one application. We have a lot of reviews coming from some domains. So we have a lot of reviews that positive or negative, for example, from book domains. We try to learn a model which can be adapted to the kitchen appliance domain. Yeah, and this is a domain adaptation problem because different reviews will have used different keywords. For book review, they will use keywords such as interesting, boring. Well, the kitchen appliance review will use high quality, leaking, broken. They use different keywords. And then previously, how can we match that? Previously, people try to use for this application, people propose an algorithm called structural correspondence learning. The idea is try to match these kind of keywords based on their mutual information, the correlation with those kind of common keywords, good or bad. So their intuition is that similar correlation will have similar sentiment here. Yeah, and then they propose their solution. Well, what I want to say here is that actually their solution is pretty specific to their application. Well, we can say actually these are just meta features. They can be viewed as meta features in our framework. And similarly, we can have intro feature characterize how this keyword appears in the document. So we can apply our framework to this kind of scenario as well. So in terms of experiment, actually, in my paper submitted to KDD recently, I actually try to I evaluate our framework in two types of different applications. One is the entity-centric document filtering, and second one is the domain adaptation idea. So basically, use a data set, try to learn a model from some domain, and then try to adapt it to a different domain. And then we compare our solution with many different kind of baselines. So for example, first, the standard learning algorithm, basically just like use traditional learning to rank framework, but use some feature we designed for that. For example, for entity-centric document filtering, I will use a lot of learning to rank feature, BM25 vector space model, and then compare it. So basically, there are LE, TOR, the learning to rank data set in MSR. So in that page, there are a lot of feature design. So I just follow that feature design to design a lot of traditional learning to rank features. Yeah, and then build this baseline. The second one is like I simply combine the meta feature and the intro features by multiply them. So much like the TF IDF, right? TF IDF, they simply multiply TF and IDF. So as this baseline, I didn't use our graphical model solution. I directly multiply two types of features. And the disadvantage of this is that they didn't fulfill the inference sparsity requirement. They will introduce a lot of noise contribution because I simply multiply them together. And this solution is a boosting framework that I proposed in my previous paper. And actually, my solution is extended. So my graphical model actually extended from this model and also output from that. And this algorithm is specifically designed for the domain adaptation. So yeah, so we can see that we also can achieve the similar domain adaptation, the performance compared with existing work. Yep.
So as far as I know, like the ACL baseline is quite low already because people already did a lot of experiment on this data set. So
yeah.
You try to compare to the more advanced baseline, like the neural network one.
No.
And then the other baseline.
Okay, yeah, this part I haven't considered because I in this paper specifically I just want to show the possibility of applying this approach to a domain adaptation. Yeah, so I didn't. Yeah, that part I haven't looked at that. Yeah, maybe in the later experiment I can try to use more strong baseline for that. Yeah, but I just I include the comparison with the domain to this work. I just want to say it can be applied to that scenario using a more general framework. Yeah, so this is the experimental result for our framework. Yeah, so in this work, actually, we are studying a querying by entities problem, entity-centric document filtering problem, and then we propose a general framework to solve that. Yeah, so as the future work, so first, we are studying the querying by entities and querying for entities. We will try to move one step forward. We try to study their overlapping part. And also, we want to try to connect it better back to the traditional information retrieval problem. This will be the direction of our future work. So first, for the querying by and for entities, their overlapping part, we are studying the relational entity search problem. Basically, the idea is that we given some entities, we try to find a kind of other entities that is related to that according to their attribute. For example, given the Bill Gates, we can find that his wife, his education background, or his founded company have different kind of attributes for that. And right now, this kind of project has been realized in industry. For example, like Google, they have knowledge graph, and in Microsoft, they have Sartorial. This kind of knowledge-based graph idea. However, this kind of output is supported by a back-end knowledge graph. So if the entity is not that popular, then if it is not stored in the knowledge graph, then it could not be shown in the result. So in our future work, actually, what we are studying is that we try to build a lot of relational searcher for that. We try to do an online relation extraction for this kind of input query. For example, we will learn a lot of searcher. One searcher is specifically finding the wife of a person, and some education. We have different kind of relation, specific design for this person, for this type of entities. And then we can try to rank the entity according to this kind of return results. Yeah, and based on how this kind of entity appear in the web documents. So as the current progress, we have some model, try to learn this kind of ranker based on some data from the knowledge base. For example, Freebase, we use extract a lot of relational data here and then use that to learn this kind of searcher. And this is already been published. However, there are still a lot of unsolved problems. So this is what we are working on right now. So for example, in the previous work, we only work on one relation at a time. So right now, currently, we'll try to, how can we do efficiently search multiple relations together and to both improve the efficiency and accuracy. And also, how can we resolve the entity ambiguity? So given an input query, so this can be belongs to different persons. So how can we search their relations to discriminate different kind of entities? So this will be the first direction of our relational entity search. And another future work I'm working on right now is about the entity intent and passage scoring. So basically, we try to better understand the entity concept hidden inside the query. And also we want to search passage that support this kind of question answering. So the problem is how can we rank the passage according to the implicitly the entity intent hidden inside the query. So this is also a problem. Right now I'm working on actually. Yeah, so this is my work. I basically mainly focus on the entity-centric search, and I also have some other related work on some citation prediction and also social annotation. So if you are interested in other direction, we can also discuss it offline. Yeah, thank you.
We have time for questions. I guess a lot of work that we are also doing it. So probably a lot of you want to have more in-depth discussion when you are meeting with the candidates. But if there is any question, quick question.
How do you envision this in a product? For example, Excel, Microsoft Excel.
Evaluate which work actually?
All of this, querying by entities, for entities.
Evaluate that.
Not evaluate it, but how do you envision it working in a product like Excel?
Product like, okay. So for example, like the first piece of work I say, this I don't think is kind of, I propose a new problem. I just propose a new platform, a back-end platform that can be used to help other different kinds of querying for entities applications. So I'm sure, so for example, when we design different kind of projects, we can easily, for example, just write some simple query as I designed to fulfill a lot of different kind of difficult operations before. Yeah, so this can be used as a back-end support for different kind of application, online application.
So you see applications category which we can use in Excel to get data into Excel.
Yeah. So for example, actually, one example application can be simply like entity search. Like I simply find out. So we can still use keyword query, but this can be translated, be translated into our design query and then try to return the result. So this is built based upon our algorithm, our platform.
Why you will come up with the 100,000 people?
I just ranked the result. The second one maybe not good. I just ranked the most correct result. So yeah, because they also mentioned about inhabitants based on these kind of patterns I designed.
Yes, but why China is? Oh, okay.
I think it's because like it's mentioned about Shanyu.
I see.
It mentioned about different cities. So there were a lot of error, I guess. Yeah, based on some pattern instruction. Yeah, we can design some application on top of our general platform. And for our second piece of work, so I think it can be very useful, as I say, for those kind of motivating scenario I mentioned here, try to find document relevant for that. And it's also easy to get the homepage or descriptive and some text data for entity, right? So it can be used to improve the accuracy for that part.
All right, so if there's no further questions, let's thank the speakers.